I heard that you can light paper on fire with water, which I am incredibly skeptical of, because if we light paper on fire and then dump it in water, it immediately goes out. So how could water possibly light this paper on fire? Let's try a few things and see if we can figure it out, or show that it's all just a big hoax. Here's our logical dilemma. Paper burns at about 420 to 480 degrees Fahrenheit. That's like 220 degrees Celsius to 250 degrees Celsius. So how are we gonna get paper that hot when water boils at 100 degrees Celsius? It seems like the max temperature for water is going to be 100 degrees Celsius. Let's start by boiling water, and then we'll try some experiments from there. Let's fill up a Erlenmeyer flask with some water, and then we'll put it on our little grill. While this heats up, think about the phases of water. This water right here was at about 22 degrees Celsius before we started heating it. Eventually, we're gonna start to see the boil. Energy is going from our hot plate into the water, raising the level of thermal energy inside of our water so that the molecules move faster and faster and faster. We gotta get those molecules so that they reach a temperature of at least 220. I don't know if we can do that. Do you know at what temperature water boils at? It's hot. The hot plate's really hot. 100 degrees. Water boils at 100 degrees. Paper burns at 220 to 250 degrees. So will the paper burn when we put it in our boiling water? Let's try. I'm not seeing any ignition. No burns. Does that make reasonable sense to you? Paper burns at 220 degrees. The water is at 100 degrees. Should it be burning? Doesn't seem like. Now, what about the steam though? Maybe the steam is over 220 degrees. In the steam, here's the steam right at the top of our Erlenmeyer flask. I don't see anything. You see anything? Let's try it a little deeper down in our Erlenmeyer. Right by the boiling water. I don't see anything. Nothing. No burns. It's steamy, but no burns. Now, why might that be? Let's see what the temperature coming out of our Erlenmeyer flask is. 60, 80, 90. It's staying at 93. So if it's staying at 93 degrees, is it ever gonna light paper on fire that has to be at a minimum of 220? No, it will not. Do you have any ideas how we could get this steam up to 220? I got an idea. I went to the department store, got a copper tube that the steam can go through. Then I put that in a stopper right here. Let's put that in slowly to make sure there's no clogs because we don't want pressure to build up and have it explode. We'll make sure we see the steam come out before we push down on the stopper. Good, we got water coming out. That's a good sign. There it is. Can you see it? Let me push the stopper in a little more. Wow, see this steam coming out? Let's see if this steam will light the paper on fire now. Nothing's lighting on fire. Let's check the temperature of this steam. Whoa, check this out. Can you see that? The actual temperature here is only about 65 degrees. It's cooled off from the about 90 degrees of steam here to about 65, 70 degrees here. Why is the steam getting colder by the time it gets out? So we gotta find a way to really heat up this steam. Here's one little science tidbit. We normally call all that we see here steam. It's the steam that is recondensed because it's lost energy and is going out of the steam phase. Real steam is invisible. We don't even see it. So I gotta try to heat this coil up and we'll see if this becomes invisible and we can get it really, really hot to light our paper on fire. To do this, I'm gonna use one of my favorite chemistry tools, the Bunsen burner. I'm gonna close it so it's ready to be lit and turn on the gas. Hear the gas coming out? Let's light it. Poof! Okay. We'll position this right underneath our coil. I'll try not to cook my hand. Now a good Bunsen flame has a little cone inside of a larger cone. Almost immediately, that water vapor coming out becomes invisible. It has actually become steam now. Ooh, look at this. See it starting to turn orange? Wow, I bet that's really hot. Now for our main test. Paper burned with water. Do you think it's hot enough? Here it goes. I'll start kind of far away and move it closer. Whoa! Immediately, you see that? Immediately it's starting to burn it. That's incredible. This is water moving through a hot coil, and this invisible steam just immediately started to burn it. Let's do some more. Hi. That is so neat. Well, let me hold it. I'm gonna hold it in place for just a second. Let's see what happens. Burns right through. Whoa. I never thought about this. Incredible. Look at that, cooking paper with water. That's incredible. Look at, here's the source. Water, just boiling water. Moving through our coil that is so hot. I can't believe it. We're burning paper with water. I'm flabbergasted. That's just terrific. Did you think we were going to be able to do that? I wasn't sure. We just cooked paper with water. Well, let me try to explain in a picture what's going on so we can thoroughly understand what's happening with the energy of our water molecules that allow it to burn the paper. If the energy of water is measured by temperature is our y-axis, then at normal atmospheric pressure we see that water is a solid below 0 degrees Celsius and becomes liquid above 0 degrees Celsius. Our water is about 22 degrees Celsius when the experiment starts, so it's in the liquid state. As the Erlenmeyer flask is heated on the hot plate, the temperature rises as the water molecules move faster. Eventually, the liquid state reaches a max temperature of 100 degrees Celsius, at which point we have a rapid boil as high-energy water molecules leave as gas. Our goal is to get those high-energy gas molecules to 220 to 250 degrees Celsius where they could potentially ignite paper. What we see happen, though, was the steam immediately cooling to 93 above the water, as energy from the hot plate no longer reaches it. The steam rapidly condenses back into water, which we see and commonly call steam. As the hot water that is condensing moves through the tube, it continues to lose energy until it reaches the coil. The coil is likely around 800 to 1000 degrees Celsius, since that is when metal begins to glow, but below the melting point of copper, which is 1085 degrees Celsius, since we didn't see the coil melting. The water gains a tremendous amount of energy in the coil and emerges hot enough to burn paper, so it is likely above our 220 to 250 degree mark. One thing I'm curious about, if this is water coming out or just hot air. Let's see if it recondenses on a glass beaker or not. Water should recondense. Let's try. Oh, whoa. Wow. See that? Immediately recondensed. It is actually water coming out. It's not just hot air. Well, how surprising. It's not a hoax. You can actually burn paper with water, and it is actually water coming out. That is really, really cool. Let me show you this cool little side note. There's this black stuff that forms on the copper coil. I don't know what it is. I think it must be some kind of charcoal byproduct from the natural gas burning, but you see it chipping off as it dries. Let me drop some water on. I did that earlier, and it was pretty cool result. Let me show you. Let me move the Bunsen. See that? Just falls right off. Cool.